All right. So again, you have your circle. J and I are 2 points that just to distinguish between being inside and the interior, and then also on the exterior. Talk about a point of tangency, things like that. Okay. A diameter is considered a chord. Okay, because it has endpoints that are on the circle. But more specifically, the diameter goes through what other points? The center. So that's why it is called a diameter, because it goes through the center. Now, circles Q and circle P are called tangent circles. That means that they intersect at exactly one point, and you see that point right here. Okay? R is called your point of tangency. All right, they touch at exactly one point, and they have a common tangent. Okay, line RS. As you see, circles T and V intersect at 2 points, X and Z, those 2 points there. And then you have concentric circles. Everybody say concentric. That basically means they have the same center. So basically one circle inside of another circle. Okay? One circle inside of another circle. Now, these are these three and even these two types of circles you may see throughout this unit. They have certain types of circles have tangents in common, okay, called a common tangent. If you look at this one here, you have this one common tangent. But there are also 2 other tangents that they have in common, okay, that you can actually draw. They're not on the picture just yet. We're going to draw them in. Now, a tangent touches a circle how many times? Once. So, for these 2, you can have another common tangent. I'm going to do my best to try to make it. You can have one here, and you can also have a common tangent here. Okay? So it's a line that touches the circles, both circles, at one point. Okay? So when you have circles like these, they have 3 common tangents. Okay? These 2 types of circles, how many common tangents do you think they're going to have?
2.
They're going to have 2. They're going to have one that runs along the top, and then one that runs along the bottom. Maybe you guys can do a better job than I'm doing. My hand's shaky for some reason. Need some more water in my life. Okay? But they're touching the circle at 2 points. Okay, so the common tangent. What about concentric circles? How many common tangents are they going to have?
Yeah.
They're going to have 0. Because there's no way I can draw a tangent to touch each circle at one point. No matter what I draw, it's going to go through one of the circles, or not through both of them. Does everybody see that? So there are 0 common tangents with concentric circles. What about 2 circles that aren't touching at all? How many do you think they're going to be? 2? 4. Why do you say 4? Because you can go between them. So you have the one at the top. That's supposed to touch.
That's nice.
You can have one at the bottom. That's supposed to touch. Shut up. And then you're going to have the one that goes through them, and then the other one. Okay, so draw your circle, draw your tangent lines a lot better than I'm drawing mine. Okay, but
Mine is supposed to be straight.
they are supposed to be straight. Touch up. Okay, so there you go. But yes, those two circles that do not touch each other are going to have 4 common tangents. Okay, the 2 in between and the 2 that run along the outside. Okay. So let's look at a few theorems here that deal with tangents, okay? The first one says that if a line is tangent to a circle, then it is perpendicular to the radius drawn to the point of tangency. Perpendicular means what? 90-degree angle. So when you have a tangent line, wherever the radius hits that point of tangency, it creates a 90-degree angle, okay? That's going to be very important when it comes to maybe some potential triangles that are drawn, and maybe finding some radius lengths or something like that. That's going to be very helpful. And vice versa. in plane, if the line is perpendicular to the radius, and its endpoint on the circle, then you know that line is indeed a tangent, okay? So if it doesn't say that it's a tangent, but it says there's a 90-degree angle here, you know automatically that that's a tangent line, okay? This one, I like to call it the ice cream cone theory, because if I were to turn this upright, it looks like an ice cream cone. Yes. Well, it says that if two segments from the same exterior point are tangents to the circle, then they are congruent. Okay? Ice cream cone theorem. As two segments from the same exterior point are tangents to the circle, then they are congruent. And I know you see this proof. We're actually going to do this one. We are going to do this one because it's just refresh your memory. So here we go. We always start with what in the proof? The given. So circle P. You want a shortcut for circle? It is a circle with a dot in the middle. You gotta include the dot if you're gonna do the symbol, okay? So, circle with a dot. P and tangents, SR and ST. Okay, we're trying to prove that those two are indeed congruent. And remember, when we're trying to prove a theorem, we can't use the theorem anywhere in our proof. Okay? So, does everyone's picture have a line from P to S? Okay. Well, since we already have P to S, could we possibly draw in some more segments, maybe? Yes, like what? The radius. Okay? So that's what I'm going to do. I'm going to draw in PT and PR. And the reason why I can do that is a postulate we learned a long time ago. That through any 2 points is exactly, no, through any 2 points is exactly one line. That's why we're able to draw these in here, okay? So that's your reason. Through any 2 points, there's one line. So let me draw these jokers in here. Okay? Now this should look like something that we've spent a whole month on. Triangles. Mm-hmm.
Oh!
Yes.
Angle PTS is right angle, PRS is right angles.
Yes. You know that angle PTS and angle PRS are right angles. And how do you know that?
Theorem 10.1.
Theorem 10.1, which basically said if it's a tangent and it hits the radius, it's perpendicular. So I'm going to basically abbreviate this. So tangent hits radius and perpendicular. So if I have right angles, think about it. I got to state that they're right angles, and then I have to state that they're what? Congruent. Y'all shouldn't have forgotten about this, hands. Y'all shouldn't have forgotten about this, okay? So you need to state that they are congruent. And besides Bryson, why?
All right.
Okay, making sure. Y'all remember something. Yes, all right angles are congruent.
That's valid. I want you to try to do this.
We gotta say a few more things. All I know right now, I'm trying to prove that ST and SR are congruent. Before I can state anything else, I gotta something else that you see that can help me in proving that those two segments are indeed congruent.
Side angle side. Dang it.
Reflexive. What's reflexive here? that is reflexive property. Okay, very good. Now, just so people aren't, so people won't think this is the case. I'll erase this. This is what we're trying to prove here. So we don't know this just yet. But I do know that PS is congruent and PS is a reflexive property. I need one more thing before I can state that my triangles are congruent. That's after. That's after you prove that triangles. Yes. Huh? How? So I need one more piece of information. All I know is I have a right angle here.
Angle TPS is near the RPS.
How do you know?
I don't.
Okay, so we can't use it. You gotta tell me a reason. It's something that's so simple. Something that's so simple. Come on, look at the picture.
Wait.
It's either got to be another congruent angle or congruent segment.
PT is congruent to PR?
Why?
Because radius, I don't know, something about a radius in the center is, I don't know.
What do you know about a radius in a circle?
They're all congruent.
They're all going to be the same no matter where you come, no matter what point you go to. So yes, PT is congruent to PR because all radii are congruent.
All what?
Radii are congruent. The plural form, radius,
That's two eyes.
that is two eyes. Yes, that's the plural form.
And now.
And now we're almost there. We got two more things. Two more things. Why you didn't have all that space?
Real space.
Good God. Right too big.
Angles, sides.
What reason? Why are these two triangles congruent?
Side.
There's no such thing as angle. Yeah. Oh snap. Yeah. There's no such thing as angle side side.
I was just thinking that like,
You're right. It is that one, but it's not called angle side side. It's called
base. Angle side.
not AL,
HL.
HL. HL.
Population.
So step 7 is the two triangles are congruent. He said it. He was like, oh yeah. Oh no.
I wasn't even paying attention. I just saw an angle and then I was like, angle side.
Oh. HL. Remember, that's only used for right triangles. Now we can state that SR is congruent to ST and Y.
CPCT. That's
CP, CT.
So basically, we're not.
This is the only proof. It's the flashback for you, really. But there you go. Okay?